So, hi everyone. This is Piyush. I'm not really from a physics background. I usually work on machine learning and applied machine learning problems in different domains. But I have been working on this type of data and this project for a couple of years now. I'm at the Lawrence Livermore National Lab near the San Francisco Bay Area. And today I'm going to talk about Pion reconstruction and the Atlas detector using GNN models. Dhanush is one of the people I work with who is a part of Atlas, and he's actually attending the meeting in person. Um, so yeah, anyway. So let's see. So just to make people familiar if they don't know about the detector geometry of the Atlas detector. It has a bunch of different types of detectors. There are like electromagnetic and hadronic detectors, which have different layers in them, and then the detectors are distributed across the barrel, and then there are detectors in the end cap and stuff like that. And each of these layers have different granularities, geometries, and so on. So the data we've been working with is mainly simulated data of single pion showers, neutral and charged pions, and we use something called topo clusters as input to our models, which are I'm guessing most of you are again aware are 3D objects that represent local particle clusters. So we are not using the whole event data, but it's clusters of data, which could be, we could have multiple clusters for any given event of a pion shower. We've previously used image-based representations of this data with CNN type of models for mainly solving a couple of problems. One is the classification of pion, like which type of pion is the shower generated from, and the other is how much energy does the pion deposit into that particular cluster that we are looking at any time. Here you're looking at a couple of examples of, well, these are average images of neutral and charged pions in one of the EM layers, electromagnetic layers. And this is just a difference between the two to get a sense of, how different they are from each other. So, like I said, we used representations like this for our CNN model previously. And we had to, I won't get into the details of the CNN model. They are in the pub note that we released about a year ago now. But then we had to work around ways of, different dimensions of images that were coming from each of the layers, because like I said, the granularity of the different layers is different, is varying across the calorimeter. So we did get really good results from our image-based models for both classification, calibration of the energies. Here you're looking at a comparison of the classification performance with the baseline method, this EM probability in red, which is, I guess, if I'm not wrong, been used for several years now at Atlas for classifying different types of pions. And the three other lines that you're seeing in this plot are the performance of the three different deep neural network models. One is a fully connected neural network, which is the DNN. There's a CNN network, and there's another convolutional type of network called DenseNet that we used for our classification. And you're looking at a plot of um, uh, neutral pion rejection as a function of the charge pion efficiency on the top here. And at the bottom here, you're looking at the ratio of the performance of the different deep neural network models, image-based models, um, to the baseline model in red. And as we can see, we see a very significant improvement in the classification performance uh, using the deep neural network models. And then the second part of um, the the task was to do regression. So We used two different models. One model was doing the classification task, and then based on the output of the classification model, we uh, we used another model to which was trained on the regression task to predict the energy that was deposited in the cluster. And uh, here you're looking at the response of the regression model, and by response medium I mean the curves are a ratio of the predicted output versus the true output as a function of the true output, the true energy. um, and again we are comparing it with the traditional baseline methods, which are the EM and LCW scales, for the charged pions on the left and neutral pions on the right. And again, as you can see, the deep learning model showed a very significant improvement in the response. And the curves you're looking at here are medians of a 2D histogram, if you may, in this response medium true energy space. So there is a distribution in both the X and Y axis, a spread in both the X and Y axis of the response. To quantify that spread, so we look at first the response median just to see what the median of the response is. And then we quantify the spread using something called interquantile range, or IQR. Um, and this is a measure of the spread of the response um, in the true energy dimension. And again, what we have observed is the spread is much uh, smaller when we use our deep learning models. And especially we see an improvement at the lower energy levels, which are more harder to predict on for the baseline methods that they have been using for several years. Now, we see great results with the image-based representations, but there are a few drawbacks of this representation, as you might have guessed. The images themselves are really sparse. Most of the pixels in the images are just blank or empty. And then, like I said, depending on which layer the data was coming from, the image has a different dimension, and you have to take care of that, and design your networks to somehow incorporate that in the model. The other issue with using images is that you're restricted to a small range of the detector, because even for any particular layer, um, the dimensionality of the images, or the granularity of the detectors changes as you move away from the center. So that's why you see this eta range restriction of zero point 0.7, less than zero point 0.7, when we use the image data. So all the results I've presented till now have been in that range of the detector, which is mainly restricted to the barrel range. So after this, we've moved on to using graph representation of the data, and there are definite certain lot of advantages in representing the topo clusters as graphs, because you can handle non-uniform 3D structure of the data, where those the types of cells of the calorimeter are different, and they have different sizes. They're coming from anywhere in the um, in the calorimeter geometry, and then we can get improved performance of classification and energy calibration in different regions of the calorimeter, the barrel regions and the end caps and the forward region. So that's why we moved on from using images to graphs. Um, the way we represent our data in graphs is um, the cells of the topo cluster. By cells, I mean these cells that you're seeing in the images, right? So these are individual cells in each layer of the calorimeter. So each cell is represented as a node, and the node features that it has is basically the energy what is deposited in the cell, and then which sampling layer did the cell come from, which layer of the calorimeter did the cell come from, what is the location of the cell in eta and phi, and the dimensions, the third dimension, and then what is the size of the cell, again in eta and phi. how big the cell was in the 8 and 5 dimension. So these were the features of the cell that were input as the graph. The edges were basically defined by the geographical locations of the connections between the cells. And this was like a one hot encoded vector, which just basically tells you, oh, cell A was previous to cell B in the first EM layer, or cell A was the next cell to cell B in going from the EM layer to the hadronic layer, something like that. So it just gives you a geographical connection between the data, and this gives you a nice structure to the graph, which is defined by the actual geometry of the calorimeter, and not really based on any heuristic like KNN or any other measure to um, um, or even like a fully connected graph, which would be really expensive to compute. Um, and then we also had a global node, which learns from, like, aggregates data from all the nodes and edges, and that just had there was just a single global feature called the total cluster energy, which is basically the total energy deposited in the cluster, the sum of all the cells in the clusters, basically. Um, and similar to the previous image representation, our target was a classification target. Which type of pion is it? Is it a neutral pion or a charged pion? And the other target was what is the energy deposited in the cluster. So that's how the graph representation was created for the data. And now I'll briefly talk about the model we used to learn from this representation. So I've been using something, the GraphNets library by DeepMind. I don't think most people are aware of this because it's not really actively developed or widely used. I think the DeepMind has moved on to um, JAX and Giraffe graph libraries, I think, if I'm not wrong, for their actual models. But then this particular library is very, like, it's highly customizable and has very, it's a very lightweight library, and it has a very simple implementation of certain graph blocks, which are easy to understand and work with. And at the lowest level, it's written on top of TensorFlow, basically. Um, it was eventually written on top of TensorFlow when DeepMind was bought out by Google. So in our models, we use something from the library, what they call a full GNN block, um, and this is how this is like a pictorial representation of that block. And what we're seeing here is you have an input graph which has the nodes, edges, and the globals as I described before. And you have an output graph which updates those nodes, edges, and globals, and spits it out. Um, what the full GNN block does, it has three MLPs, fully connected multi-layer perceptrons. There's an edge MLP, a node MLP, and a global MLP. The first step is you know uh, concatenating features from edges, nodes, and globals, and sending it to the edge MLP. And this happens at every edge. And the edges can either there are flags that tell do I just want to look at which node do I want to look at? Do I want to look at both the connected nodes, or do I want to look at only the receiving node, or the node the edge is sending to? So that's the first step. Once that data is passed through the edge MLP, it's aggregated using a permutation invariant aggregation function like a mean or a sum. That feature is sent to the node MLP after, again, concatenating with the node features and the global features. Again, this is done for each node, and pass through the node MLP. Again, then another aggregation function over the nodes, and then a global MLP, which looks at the global features and the incoming features from the previous two MLPs, um, and spits out the global update. So at the end of this, you see an updated graph, which has a new set of features now, which is learned from all the input graph features, the nodes, globals, and edges. So this is one block in the network. This what you would call a one step of message passing in the network. And you can, based on how these MLPs and globals and nodes and edges are connected to each other, you can form different blocks from this fully connected generic block. You can convert it into an interaction network block or a deep set block and so on and so forth. They have a full paper on this, which describes how they can be interchanged within each other and detailing the basics of graph neural network. Anyway, so this is the one step of message passing, like I said, in the network, in the model. The model itself that we used looked something like this. So you have the initial cluster graph as the input, followed by there are four of these. Oh, that's a number missing. There are four of these um, full GNN blocks, and then this model is actually performing the classification and regression um, simultaneously. So after the data has been passed through the GNN blocks, we only use the global readout, so only the global feature at the output of this GNN block 3, and use that and pass it through an MLP first to predict what type of pion was it. Was it a charged or a neutral pion? And then there's another stream of data that uses that global output, concatenates that with the output of the classification, um, and passes it again through a dense network to predict the energy of the cluster, the energy deposited in the cluster. And the reason to do this is give the model additional information about the type of pion it's going to make the energy prediction of, right? And these connections that you're seeing here are similar to what you would call residual connections, just that in the case of residual connections, the features are added, the previous step features are added to the new step. Um, in this case, these are concatenations. So you have, say, the node features here has a length of 64 and the input was a length of 8. The output here after concatenation will be a length of 72, and you keep doing that through your network just so that your network has information of all the previous steps, um, previous features uh, that were seen through the network. And similarly, in the end, we also do a global concatenation of all the features. So at this point, the globals have all the global features across the four blocks, and then the input global feature, which was the cluster energy to begin with. And then to balance the output of the loss of the model, we have this alpha value which balances between the regression loss and the classification loss, and uses combination of them to learn from. We used small subsets of data to and ran a few hyperparameter combinations. We ran sweeps through a few different hyperparameter combinations to get the quote unquote best value for alpha, and like the number of layers in the MLP, the number of neurons in the MLP, the number of GNN blocks that should go in the model, so on and so forth. So we ran a bunch of different hyperparameter sweeps to get a sense of what would work best. There wasn't a lot of difference between them, but there were subtle differences that I guess helped us get the best results with the data that we were working with. Anyway, so moving on to the results of the model, uh, we'll first look at the classification results. And on this plot here on the left, what I'm showing is a comparison of the classification performance of the GNN with the previous CNN model that I previously described, the image-based approaches. And this is only in the eta range less than 0.07, because the image-based models were applicable only in that region. So we can see from this graph that the CNN model, which is in this light greenish color, um, is a little worse than the graph ML model. So the graph ML model does show an improvement over the CNN model. Um, the deep sets model is another type of graph network that we've been working in. I'm just showing one of the results that we've been working with, that I particularly worked on. There are other collaborators that work on different types of graph networks. So And this is one of the other networks that we worked on. And again, we are seeing at the ratio here compared to the baseline performance, which is in green here, same as before. And we do see a significant improvement in the graph model performance compared to both the image-based model and the baseline model. And all of this, like I said, is in the restricted eta region. Uh, the graph models actually perform better in the whole eta region when it's expanded out to the whole calorimeter as well, which was very encouraging to see. And this is like the biggest advantage of graph models, that we could train models with data that was coming across the whole data region and not just restricted to a smaller subset of the data. And again, we see a very significant improvement in the performance compared to the baseline model in both the graph implementations again. So that was the classification performance. Here is the regression performance of the model. Again, the EM and LCW are the baseline methods that are currently being used in Atlas. They're not machine learning based. And what you're seeing in these three plots is the combined performance across the whole data set, including the neutral and charged pions, then just the charged pions and just the neutral pions. Again, we're looking at the response medians here, meaning the ratio of the predicted output to the ground truth output as a function of the ground truth energy. And again, we see a very significant improvement in the performance with the graph network models. And all of this data is in the whole eta less than 3 region. So much more expanded region than the image-based models. And similarly, with the IQR plots, the interquartile range, the spread of the predictions is much tighter in the case of the GNN model outputs. So yeah, so that's the final set of results I have. And what we're planning next is basically incorporate and track data in our graph-based models. We do have some results on this, but they haven't been reviewed and released for to be shared, basically. So I can't do that. And then the other thing is using these trained GNN models for inference in the Atlas software framework, Athena. Which involves conversion of the model into Onyx and and implementing it in the Athena framework. We've done this before with the image-based models. Dhanush was the one who actually worked on that, and we are planning to do that with these graph models as well in the coming months or so. And that I think I'll end my talk.
Thanks, Piyush.
Okay. Yeah, so I don't know if anyone has questions.
Anyone?
Let's see.
Hi, this is Giuseppe. You hear me?
Yeah, I can hear you.
Yeah, so a question about the globals. So your starting point for the globals is just the cluster energy, right?
Yes.
But then to slide 7, because that's directly related to the regression, right? But it's not directly related to the classification. But I guess as the network progresses, you keep concatenating the globals, so it's adding information that allows the regression as well. Is
yes,
that the idea?
that's true. And even though we are only using the globals at this stage, we are actually basically throwing out the node and the edge information after this stage of the model. But then the globals are learning from the nodes and the edges, and they are really important for which type of pions they are. Is it a charged or a neutral pion? Because if you the neutral pions tend to shower and decay in mainly in the EM layers, whereas the charged pions go on to the hadronic layers and stuff, all the way to the hadronic layers. So the global features at the end of this step in the model have all that information incorporated in them, and therefore can be used for classification as well, and not just the regression.
Thank you.
Okay.
Yeah, I might have missed this, but what are the sizes of the graphs, just characteristically?
So every MLP in this block is a 4-layer, 64 neurons in each layer, fully connected network. If I'm the total, oh, you mean the size of the graph?
Yes.
They can range actually anywhere between 10 to 15 nodes to a few hundred nodes.
And how many edges typically? How connected?
On an average, I think each node has 4 edges, based on the geometry of the detector and how we've used that. Each node has 4 edges, so much less than the total number of fully connected edges there would be. But yeah.
Okay. Thanks again, Piers.